Good afternoon. Thank you for joining us, and a very warm welcome to this latest in our series of Saints Talks from the University of St Andrews. This one entitled Our Dynamic Sun, Creating Mathematical Models to Understand Our Local Star. My name is Alex Hayes. I'm Head of Development for Arts and Divinity here at St Andrews, and in that capacity I'm particularly ill qualified to introduce one of the university's most distinguished mathematicians, Professor Ineke de Moortel. Ineke is Professor of Applied Mathematics in the School of Mathematics and Statistics, and her research focuses on the dynamic processes occurring in the Sun's atmosphere. In particular, the behavior and interaction of Magneto HydroDynamic waves and oscillations in 3D geometries, using both observations and computational simulations. In 1997, Ineke completed a master's degree in mathematics at Katholieke Universiteit Leuven in Belgium, which included a brief stay at the University of St Andrews in 1996 as an exchange student on the Erasmus programme, RIP. She completed her PhD in solar physics in 2001 at St Andrews, where she remained as a postdoctoral research fellow, becoming Professor of Applied Mathematics in 2013. Our sun is literally bursting with activity, and a range of satellites is now observing it in unprecedented detail, giving scientists an ever greater understanding of our local star. Frequent violent eruptions of hot matter send seismic waves across the entire sun's surface, like huge solar tsunamis, while highly energetic particles stream continuously out from the sun, punctuated by massive blasts of hot plasma. It all sounds very exciting, but what does it have to do with us? And in showing us how all this solar activity affects our daily lives, Ineke is going to take us from deep inside the sun's nuclear core, through the solar surface, into its atmosphere, on towards Earth, and finally out into space, showing how scientists use satellite technology to create mathematical models of this solar activity. She will speak for about half an hour, after which you'll have the opportunity to ask her questions, and I do warmly encourage you to do so. Please submit your questions in the chat bar on your screen, and you can do that at any point during the talk or afterwards. We'll wrap up promptly at 6:15, so please don't miss your opportunity to ask any burning questions. When her attentions are not turned towards the sun's activities, Ineke can be found enjoying the more earthbound delights of the Scottish hills, where she's completed the ascent of all 282 of Scotland's 3,000-foot Munros. A keen sailor, she's also a dinghy sailing instructor at St Andrews Sailing Club, which combined with her academic interest seems to me to rather neatly complete the elemental triptych of earth, wind and fire. And I think that's more than enough from me. So on that note, I'm delighted to hand over to Professor Ineke de Moortel for her Saints talk on our dynamic sun. Ineke.
Thank you so much, Alex, for that kind introduction, and thank you everybody for joining us. Where hopefully I will take you on a trip through the layers of our sun, and I promise I will keep it light on the mathematics. But I do want to show you some of the models that we create here and how they help us understand our local star. So let's start at the beginning. The sun is, as a star, a pretty ordinary star. It is a middle-aged star, roughly about halfway through its lifetime. But of course, it is special to us. It resides in one of the spiral arms of our local galaxy, but it is close to us, providing us with the light and warmth and energy to sustain life on Earth. But as an astronomer, it is also the only star that I can see in a lot of detail to study the processes that are going on, and hopefully you'll see some of those later in this talk. As the introduction said, let's start deep inside of the core of the sun. The inside, or the interior of the sun, is usually divided up in 3 different regions. We have the very dense and very hot core, where the nuclear reactions take place. Above that, we find a zone that is generally referred to as the radiative zone. And then about the outermost third of the interior of the sun is a convection zone. And here we find hot material essentially bubbling, as you would see in any liquid that you boil, with hot gas rising to the surface and then falling down again. Now, most of my talk is going to focus on the atmosphere of the Sun, but I will come back to this convective layer just below the surface. Now, the temperature inside the Sun in the core is about 15 or 16 million degrees, and then as you journey out towards the surface of the Sun, it gradually gets cooler, as you would expect as you move away from any energy source. Now, moving out from the interior of the Sun, we come to the region called the solar atmosphere. The solar atmosphere starts at the solar surface or photosphere. Now, the Sun is entirely made of gas, and so there is no well-defined surface. Scientists call the layer the surface, which emits white or visible light, which is of course the light that we are all attuned to be able to see here on Earth. So we call that layer the surface, which is at a temperature of about 6,000 degrees. Now, what's strange on the Sun and on many other stars is that as you journey further out, the temperature starts to climb again. We come to a region often referred to as the chromosphere, where the temperature rapidly climbs from about a minimum of around 4,000 degrees all the way up into 1,000,000 degrees, and then further into several million degrees in the outer atmosphere or corona. Now, the movie that's been cycling on the right-hand side of the screen cycles through these layers, starting with the photosphere, coming into the chromosphere, which is hotter, and then the outer layer, which emits into extreme ultraviolet, but also gamma rays and X-rays. So one more time, this is a photosphere where we see sunspots, then the chromosphere, hotter layer, and eventually emitting in extreme ultraviolet and X-rays is the corona. Now, there's one layer in the middle here, which I didn't say anything about yet, but that's this layer here with the black and white features that you can see. These features indicate regions where the magnetic field is very, very strong. And as you look through the movie, you will see that these regions coincide with the very bright emission in the outer atmosphere. So to summarize some of that, on the next graph is a graph which depicts this coronal heating problem. So if you look at this horizontal axis, this gives us the distance above the photosphere or the surface of the Sun. And then on the vertical axis here, we're displaying temperature. And you can see, if you follow this blue line, that the temperature climbs from a few thousand degrees all the way up into the millions. Now, from the previous movie, you can see that we know as scientists that these bright and hot regions coincide with strong magnetic field regions. The magnetic field, we know, is generated inside the interior of the Sun, and we think the layer where this magnetic field is generated is this layer between the convection and the radiative zone. We then think that the magnetic field rises and eventually breaks through the surface, where it makes the nice big coronal loops and sunspots that we'll be looking at in this talk. There's a schematic here at the bottom which illustrates how we think this happens. So we start with magnetic field line rising through the surface, but because the Sun is made of gas, the Sun does not rotate as a solid body. The Sun experiences what we call differential rotations, and some regions of the Sun rotate faster than others. In particular, the equator of the Sun, the region here in the middle, rotates faster than the two poles, so the north and the south pole of the Sun. So as this field emerges and the Sun rotates differentially, this magnetic field starts wrapping around and becomes all tangled up. And again, this will be important later on in the talk. But for now, let's just have a look. So we know that the magnetic field is generated in this schematic at the bottom of this picture, at the boundary between the radiation and the convective zone. And we then think it breaks through the surface to form these huge magnetic loops that are illustrated here. And this is a little bit like the arcs that would be formed by iron filings if you put them around a bar magnet. The region where the magnetic field breaks through the surface, those are the regions that we know as sunspots and which I'm sure many of you are familiar with. So sunspots are regions on the sun's surface where the magnetic field is very, very strong. So we get these huge magnetic arcs, but I want you to remember that actually the foot points or the legs of these arcs are still anchored below the sun's surface where all this convection takes place. So this is just an observation. On the left-hand side of the screen here is a full disk observation of the sun in visible light, and you can recognize the sunspots as these little black dots. And these, as I've said on the previous slides, are regions of very intense magnetic field breaking through the surface. On the right-hand side is a very high-resolution image taken with a ground-based telescope of this particular sunspot. And this is to illustrate the enormous detail that we can see in these observations, but also to give you an idea of scale. I have put on the top of this image an image of the Earth to scale. So you can see that what we're referring to here, these black features, what we're referring to as spots, really are enormous regions of intense magnetic field, many of which are the size of the Earth or even bigger. So this is one image here taken by a ground-based telescope. On the next slide is just a gratuitous extra image from a new telescope which is built on Hawaii and which came online taking its first images nearly 2 years ago. And again, you can see the incredible detail that we can see in these sunspots. We can see the kind of darker region here in the middle, and then as the magnetic field fans out around the edge, we can see what's called the penumbra. Now, for now, I want you to actually look at the pattern right outside the sunspot, this kind of honeycomb-like pattern at the edges. This pattern we find back all over the sun's surface where there aren't any sunspots. And what this pattern shows is the top of the convection cells that we talked about earlier. So the bright bits in the middle are the regions where the hot gas is rising, and then the edges, these darker lanes, if you want, are the regions where the gas is sinking again. And this, although this is just a still image, this is a very dynamic process. So these convective cells are constantly bubbling away, buffeting around and changing. And this you can see in the movie on the next slide. So we can see the sunspot, but then as we zoom in, you can see in this movie how there's this constant buffeting and changing of all these granulation cells. Now remember, the magnetic field is still anchored below the surface with its feet firmly in this granulation pattern. So not surprisingly, the magnetic field will constantly be buffeted around. So far I've only shown you this schematic of these magnetic loops that break through the surface, but here on this slide is an actual observation. This observation is taken in extreme ultraviolet, so it's taken from space, and it outlines the hot gas that is trapped on these giant magnetic loop-like structures. So the gas in this particular observation we know is around about 1 million degrees. So we have these giant magnetic loops, and I show you a nice example here as an observation. But these loops are everywhere in the sun's corona. So this is a full disk image of the sun's corona taken quite a few years ago. And you can see that there are these bright regions everywhere throughout the sun's surface. And when they are kind of concentrated in one of these regions, we refer to this as an active region. Now, I'm sure many of you have heard about the sunspot cycle. At any given point, there are a number of sunspots visible on the sun's surface, but this number varies over time. And you can see an image here starting actually in 1700 and coming all the way up to the present day, where observatories have recorded the number of sunspots visible on the sun's surface every day. And you can see that this cycles in a fairly regular pattern throughout the years. And in fact, for the sun, we know that the number of sunspots varies on an 11-year cycle. So every roughly 11 years, the number of sunspots is at a maximum, which we refer to as solar maximum, and then gradually the number of sunspots becomes less and less until we reach solar minimum. And you can see this is the year 2000 here, indicated here. And at the present day, we have just come out of a solar minimum, and the number of sunspots that is visible on the surface is starting to climb again. And we expect to reach the peak of the next cycle in a few years' time, probably around 2025. So, as the number of sunspots varies, it won't surprise you that the way the outer atmosphere looks varies as well. So this is just a number of snapshots, again, of the full disk of the sun over the years, starting in a solar minimum, this particular one in 1996, coming to the next solar maximum around here in 2001, and then going down again to solar minimum. And you can see how the outlook of the sun changes quite dramatically, looking very exciting and full of features near solar maximum, and somewhat quiet and dimmer near solar minimum. Now, it's important to emphasize that even around solar minimum, the temperature of the outer atmosphere is still several million degrees. Now, I said at the start of this talk that I would talk about the mathematical modeling, and I'm going to take this opportunity to just interrupt this talk with only 2 slides showing the mathematical equations that underlie our modeling. The equations we use, as Alex said in the introduction, are referred to as the Magneto HydroDynamics equations, or the MHD equations for short. Now, these equations are a combination of Maxwell's equations describing the behavior of magnetic fields and the fluids equations. So the variables we deal with are the normal variables you would expect when dealing with a fluid. So things like the density, the velocity, the pressure, but also the temperature. But also the variables you'd expect when dealing with a magnetic field. So the magnetic field, the electric field, and the current density. These variables are then combined into equations, which I am going to show you on the next slide. So these are a complicated set of equations referred to as the MHD equations, which tell us how all these variables change in time and in space. So I'm not going to go into derivatives and into the details here, but we have derivatives, which tells you how variables change both in time, but also, for those of you who recognize the symbol here, in space. So generally, these equations tell us how things behave as a number of forces take place. And as an example, this particular term here tells us the change in pressure. And we all know that a change in pressure leads to a force. We know that, for example, if you look at weather charge, where the pressure change is rapid, you get stronger winds. So similar to, for example, these kind of charts, we know that these forces will change our variables. Now, most of the time, we use large-scale computational simulations to solve these equations. So one more movie, and then I would like to show you some of the examples of this modeling. This movie is a composite movie of a few different parts. So on the left-hand side, we have the full disk of the sun as it rotates for a few days. The sun takes about just over a week for a full rotation on this of an active region on the disk that you can see here. So we're following this active region for a few days. And then at the top right here, you can see a zoomed in image of this particular active region. On the bottom here is the magnetic field that would be underlying this active region. So this is what would be visible in a white light observation of the surface of the sun. And this at the top is what's visible at the same time in an observation taken in extreme ultraviolet wavelengths. So you can see that as the magnetic field changes very rapidly here, you get corresponding rapid changes in a very dynamic looking active region. Now, the sun's magnetic field is constantly changing. We know that the sunspots on a large scale are constantly changing, but remember this granulation pattern on a smaller scale is also constantly changing. And here in St Andrews, we model both these types of behavior, both on small scales and on large scales. So this is just a few illustrations of the type of models we develop here. So remember, if I go back to this cartoon, we have our magnetic loops anchored below the surface in the convection region. And then below here, I have a few different illustrations of how these models or how our models try and reproduce or replicate the interaction between magnetic fields. So you can imagine some of these colored patches, like the white and the black, or the two white patches here, or some of the patches on this model here, represent the sunspots. And we then try and model what happens if these magnetic foot points or sunspots are either moved past each other, or maybe they rotate around each other because of the random motions, or maybe they just spin on the spot. What these models try and show us is how the magnetic fields associated with these sunspots then interact. And what happens is that currents develop. So these kind of shaded areas in blue or purple represent areas of high current that develop as these magnetic fields are interacting with each other. And currents mean heating, essentially. So these models try and determine how some of these motions, quite elementary motions, just moving past or spinning around each other, can lead to heating through the currents that are generated by these magnetic fields as they move past each other. So this would be models of trying to reproduce the very hot atmospheric temperatures that we observe. What we then do is try and compare the outcome of these models with some of the motions and the hot temperatures that we observe to try and determine whether we get the spatial and the time scales of this heating right. If not, we have to go back and adjust our models again. Now, these are just some examples of some of the work in the solar group here in St Andrews of modeling the small scale magnetic field. Now remember, the scale here, one of these sunspots is easily the size of the Earth. So the small scale whale is really a relative term here. On the next slide is a very different example from one of my colleagues who models the large scale overall behavior of what we can call the global magnetic field of the sun. So he doesn't so much focus on these small details, but looks at, standing back, what does the overall magnetic field of the sun on a much larger scale look like? And this type of modeling is very important when we want to know what the effect of the sun's behavior and the sun's magnetic field is going to be in interplanetary space and also near Earth. And I'll come back to that in a few slides. Now, so far I've talked about relatively small scale and somewhat gentle motion, saying the magnetic fields here get buffeted around by the convection. Now, sometimes these magnetic fields end up becoming incredibly twisted and tangled so that eventually an explosion occurs by the buildup of all this magnetic energy. And these explosions are what we all know as solar flares. So on the right-hand side is an image of what looks initially quite a nice stable region, but you can see that there is this huge explosion here in this very bright region. So a solar flare is essentially when the magnetic field becomes so tangled that too much magnetic energy has built up and the field goes unstable and essentially explodes. So this was one movie, there's another one here. If you start watching the region in the bottom corner here, again, the region looks quite quiescent and nicely behaved, but you can see that then material is rapidly lifted up as the magnetic energy is released. But there you go. Now what we saw there was the start of what is called a coronal mass ejection. And this is where large amounts of materials are ejected from the sun out into interplanetary space. And again, here are a few still images of different coronal mass ejections. So again, you can see the start of a coronal mass ejection here about to take off from the sun's surface. So for scale, this would have been the full disk picture with this big loop of material here about to break free. And again, superimposed, so this is not in the right location, this is not where the Earth actually sits relatively to the Sun, but for comparison, this is the size of the Earth. So you can see that these are huge structures about to lift off from the Sun. There's a similar image on the right-hand side, again standing back a little bit further, where we can see the initial propagation of one of these huge coronal mass ejections into space. There's a movie here on the next page, and I'd like you to focus at this structure at the top left here. So again, you can see that this region at the start is actually quite hard to identify. It's not until the coronal mass ejection actually starts lifting off that we very obviously can identify where this event is about to happen. And these coronal mass ejections are part of what we call space weather, and you can see why they can be pretty tricky to predict. If I hadn't told you to look in the left-hand corner or at the top of this image, it would have been pretty hard to identify where this event was happening. And to be honest, I only know it's going to happen in the top left-hand corner because I've seen the movie before and I know where to look. So these regions look like they are stable for a long time, but all of a sudden an eruption occurs. And it is these type of events that we also try and predict. Now, this particular movie stands back even further, so you can see the propagation into space of these coronal mass ejections. The disk of the Sun is actually just this little white circle in the middle, and it's been obscured by a bigger disk on board of the satellite so that we can see the outer atmosphere here. And you can see from this movie that, and I'm going to go back so that it plays once more, sorry about that. You can see that coronal mass ejections happen all the time. You can see them going off in all directions, and around solar maximum, we generally expect about 3 coronal mass ejections per day. Now, these coronal mass ejections will go off in all directions, and you can see from an image like this that some of them will be Earth directed. So what's happened here, what you see at the end of this movie, for example, as well, is that the coronal mass ejection has passed the spacecraft that was observing. And what you see here is all the energetic particles hitting the detector of the spacecraft. Now, these particular CMEs, in this case, was an Earth-directed one, which then also hit the satellite that was observing near Earth. Now, as well as coronal mass ejections, there's one more phenomenon called the solar wind. And the solar wind is a continuous stream of matter leaving the Sun. And the only reason you can really, or the only way you can really see it in this particular movie is by focusing on the tail of this comet. And you can see that as the comet goes past the Sun, the tail essentially flips round because it aligns itself with this wind coming from the Sun. It's very much like when you are running or walking and it is windy, your hair or your scarf or anything you might be wearing essentially flaps in the wind. So you can see that this comet tail flips round and aligns itself with the solar wind. So the question nearing the end of this talk is, well, how do these CMAs and the solar wind affect the Earth? So let me try and explain this with this schematic of the Earth. This is a schematic of the Earth in the middle here with the Earth's magnetic field coming out of the North and South Pole and making these big dipole loops, just like a bar magnet would do. Now, if you imagine the Sun to be on the left-hand side, we have the solar wind constantly streaming past us. What happens because of the solar wind is that one side of the Earth's magnetic field gets compressed on the day side, because that's the side where the Sun is, and the other side, which faces away from the Sun, so that's the night side, is stretched out into space. Now, this magnetic field protects us from most of the effects of the solar wind and solar storms. This is a cartoon, not an actual observation, but you can see how the cartoon indicates that all of the energetic material from the solar wind, but also from coronal mass ejections, essentially nicely streams past us. So you can see how we very much become a bubble inside the solar wind as the solar wind streams past us. Now this works really well as a protective bubble, apart from in two regions, and that's near the North and the South Pole. So if we move on to the next set of images, again, this is a cartoon movie to try and illustrate what happens. But if you imagine one of these coronal mass ejections leaving the Sun, arriving at the Earth's magnetic field, most of the energetic particles will stream past us, but some of them will actually enter the Earth's atmosphere near the North and the South Pole, and this we know as the Aurora, or depending where you are, the Northern or the Southern Lights. So I'll let this movie play one more time, but we get the coronal mass ejection with most of the energetic particles streaming past the Earth, but some of them entering the Earth's upper atmosphere as they stream along these field lines near the North and South Pole. Now, these auroral ovals near the North and South Pole can move further southwards during a particularly energetic magnetic storm, and that is when you start to see the aurora at lower latitudes. And the image on your left here, for those of you who might recognize it, is actually a picture taken in St Andrews. You can see the cathedral and the castle here on the right, back a few years ago when we had particularly intense magnetic storms, and you can just about make out the northern lights here. Now, the northern and the southern lights are a very pretty demonstration of solar or space weather, but it does actually have the potential to affect technology on Earth. I'm sure I don't need to tell any of you that a lot of our communication signals these days rely on satellites, and satellites are vulnerable to damage from solar storms. Either the electronics on board or solar panels can get damaged by solar storms. But also structures here on Earth, any long metal structures which can be overloaded by the electric currents that are generated during a particularly strong solar storm. And such structures are, for example, pipelines or train tracks, but also power lines. On the right-hand side here is an image of North America. For those of you who are familiar with the geography, here are the Great Lakes. So you can see this is the northeast coast of America just before and after a solar storm. And if you kind of compare the intensity of the lights, you can see that an awful lot of people were left without power for quite a long duration as a direct result of a particularly strong solar storm. This is really all I have to say. I hope you have enjoyed this talk. Before I switch to the question and answer session, I just wanted to share these images with you, which are images of the sun today. Anybody can freely download these images. They show you the sun observed only about an hour ago, actually, in a variety of wavelengths. You can see the wavelength we've been looking at most often in this talk, extreme ultraviolet, and the white light pictures of the sun are here. And unfortunately, it looks like there are no sunspots on the part of the solar disk facing us just today. But you can see that there are likely some just about coming around the corner here on the left-hand side. So let me thank you all for joining me this evening, and I very much look forward now to the questions and answers.
Ineke, thank you very much. That was absolutely fascinating and really beautifully illustrated as well. There's a lot of beauty in those images, but kind of slightly terrifying as well in terms of the scale of these energetic events. We've got some questions coming in already, I'm delighted to say. So Emmy says, do you use live data to create the models or pure mathematics? If data, do you apply for telescope time and gather new data, or do you use existing data, since it seems like there is such a large existing database on solar activity?
Thank you so much for these questions. I'll try and answer all the bits of it. So we will use a variety, but usually the data will be at least a couple of days, if not a little bit older. Now, solar physics community has a fantastic open data policy. So really, anybody can download these data if you want. We don't so much have to apply for telescope time from those telescopes that observe continuously, and most of the images I've shown you are actually telescopes or satellites based out in space that observe continuously, and anybody can have access to those data. For the ground-based telescopes, yes, we do operate with a telescope allocation time where you apply for time to run your observing program. And we do a mixture. Sometimes we just use existing data to compare our models with, but sometimes we have models which we think predict something particular, and so we ask the observers if we can run a campaign to look for something like that. So really we do a mixture of all these things.
Thank you. A question from David Wallace, who says, great talk. The mass ejections looked as if they came from string-like features. Is that right? And what's the time scale of the movie? I guess he's referring there to the mass ejections. You know, you can give us there are a number of different movies, but perhaps you can give us a sense of what sort of time scale those events happen over.
Okay, thank you. That's a really great question. Thank you, David. And I really should have highlighted the timescale of those movies. For example, the movie I played of some of the continuous coronal mass ejections, that was actually a week's worth of data compressed into a very short movie, just to illustrate for you all the point that actually coronal mass ejections happen fairly frequently. And the time it takes for a coronal mass ejection to arrive, so to travel from the sun to the Earth, actually varies depending on which part of the material you're looking at. The electromagnetic radiation arrives within a few minutes, as we know. The actual bulk or the material of the coronal mass ejection itself takes a few days usually to arrive. So again, we have a variety of timescales that we model, going from minutes to hours to weeks when you go out to longer or to larger scale features.
Thank you. And so the structures from which those coronal mass ejections emerge, are they basically the same sort of magnetic loop structures that then, which is why he refers to them as looking like string. Yeah. Sorry, I hadn't answered that. So again, yes, they are the kind of magnetic fields that somehow become unstable, and what we often see is these magnetic fields kind of rising and stretching out until eventually they're kind of pinched off at near the bottom or so. So perhaps not string-like, but loop-like, yes. But they form the kind of huge ballooning structures in 3D. Yeah, got it. Thank you. From Anonymous here, thank you for a really interesting talk with amazing images. How does the magnetic field and its variation affect Earth? So I guess the questioner is thinking sort of out with you talked about the solar storms and those effects, but I think perhaps on the more sort of normal magnetic field variations, how do they impact us?
Again, thank you for a really good question. So hopefully with the solar storms, I've given you an idea how they affect the Earth or the near Earth space environment. I talked about the sunspot cycles. You know, we see more and less sunspots, and what we do know is that 11-year cycle is present in some features on Earth. For example, you see the 11-year cycle in, for example, tree rings. So we do know that same variation is present here on Earth in some features. For example, you also see it in ice cores. How exactly that link is made, we don't know 100%. for sure, but we can see the same pattern appearing in things that grow or deposit, like ice cores and tree rings.
Thank you. And so I have a couple of questions which are essentially the same, one from Ray and one from Anonymous, but which relate to the answer you've just given. So perhaps might be able to sort of expand on that a bit. Does the sun's activity over many years affect global warming in any way? And again, the other question almost exactly the same. Is there any connection between long-term sunspot activity and global warming?
Thanks again. I think the short answer is both yes and no. As I said, we know that there is a connection between the sun's activity levels and things like tree rings, ice cores, so I guess things that depend on light and warmth. We also know that the levels of variation in the sun's activity don't come anywhere near explaining what we now see as global warming. So yes, there is a pattern. Yes, there are longer term cycles in the sunspot cycle as well. I only highlighted the 11-year one, but there are longer ones as well. But we do know that the variation in activity from the sun comes nowhere near explaining the current variation we see and know as global warming.
Okay, thank you. I've got a bunch of really good questions here, so we'll crack on. Peter says, thanks a lot for this beautiful talk. What would you say is the frequency of a huge solar storm with the size of the Carrington event in 1859, question mark, he thinks? Is that, for instance, is that a 1 in 100-year event?
Thanks again. So I'll just explain. The Carrington event is an event that actually I'm not sure of the exact date, but let's put it in the second half of the 19th century. I actually think that date was correct there. It was a huge, it must have been a huge solar flare because it was seen from white light observations. All the observations I showed in the talk of solar flares were taken from spacecraft. So they were taken in extreme ultraviolet or X-rays, and actually we also see gamma ray emission from big solar flares. We don't always see observations or evidence of the flares in white light unless they're a particularly large one. So we know that the Carrington event must have been a huge event to be essentially observed at that time in white light. Now these events happen. Are they a 1 in 100 years? Yes, probably roughly, but then remember 100 years could be anything from 100 to 500. You know, they're not frequent. As I already said in my previous answer, there is an 11-year solar cycle, but we know that there's also longer term variations on top of that cycle. So yes, these events happen. They are rare, on the order of hundreds of years.
Thank you. Yeah, I mean, you could see in the graph that you showed quite early on in the presentation, there's a very obvious long-term cycle overlying the shorter-term 11-year cycle. Yeah. Question from Trevor: the distortion of the Earth's magnetic field will vary as the Earth rotates. Does this affect navigation, which makes use of magnetic? Sorry, does this affect navigation, which makes use of magnetic variation when plotting a course?
Okay, gosh. So yes, as I said, one side is compressed and one side is stretched out. And I guess that side constantly changes as the Earth rotates because the day side always faces the sun and is the compressed side. Whether this is enough to affect magnetic distortion or magnetic variation, to be honest, I don't really know. What I do know is that planes may well alter their routing somewhat if they know that there is a huge solar storm, and to stay away somewhat from the poles if they can. But whether it affects navigation, to be honest, I really don't know. Okay,
thank you. From Lorne Macmillan, do we know why the cycle is about 11 years?
No, I think is the short answer, but also yes. So this part of modeling the behavior of the sun is done by people who study dynamos. And And we know that the sun is by no means the only the only star that has a hot atmosphere and a magnetic field. We see this kind of pattern of sunspots or star spots, I guess, as I should call them, on many stars. And the cycle is of different lengths. So we often see a cycle, but it is not of the same length. So it can be 10, 14, it can be all kinds of different numbers. For our sun, it is 11 years, and my dynamo colleagues are hard at work. They can kind of model the cycle, but the actual timing, the 11 years, is still something that's quite difficult to model. It's related to where these sunspots break through the magnetic field. At certain parts of the cycle, this happens near the equator. Eventually, this starts drifting north and south towards the pole, and then it starts again. So somehow we know that's the kind of cyclic pattern that sets that time scale. Why exactly, or why it is exactly, or roughly 11 years, we don't know. But perhaps something interesting to mention is that I called it an 11-year cycle, which it is. But every time the sun goes through the kind of minimum and maximum, the field actually reverses. So the North Pole becomes the South Pole and the other way around. So a full cycle is actually 22 years. So the field will flip and then flip again so that you're back to the start after 22 years.
Thank you. From Andrew Wallard, do you need to make radiometric or other remote sensing measurements of corona intensity for your comparisons with experiment? If so, what's the uncertainty, and are they traceable to the International System of Units, SI? Do you understand that question? Because I'm
so everything I showed you here was done by remote sensing. Okay, so most of what I showed you was done by satellite-based observations. Some of it was from ground-based telescopes. The atmosphere, the temperatures in the atmosphere are so high that the material emits in ultraviolet, extreme ultraviolet, and X-rays and gamma rays. Those emissions or those wavelengths are not observable from the Earth, from the surface of the Earth. So to see that kind of emission, you do have to go into space. What we can observe from the Earth, for example, is obviously the visible light. So the sun's surface, we can observe from the Earth. So we use a combination of kind of Earth ground-based and space-based observations. And I think all I can really say is that, well, we try and be good and measure everything in SI units. There's the occasional old-fashioned person still reverting back to a previous system, but we try and be good.
Okay, thank you. There's a question from Avril. So Avril also asked about the 11-year cycle, but also, which is a really good question, I think, does the latitude of sunspots change over time?
Yeah, thanks, Avril. As I just I've already said, at the start or the end of one cycle, whichever way you want to call the start, the sunspots will emerge near the equator. And then gradually over time, they start to drift away from the equator towards the poles. So if you would draw the position of where these sunspots are over time, you get them started near the equator and then gradually they drift away upwards and away downwards. And it is often referred to as the butterfly diagram, because if you do it going from both directions, from the equator towards the poles, and in time, you kind of get these drifting structures, these diagonal structures on both sides, and it looks like the wings of a butterfly. So it's called the butterfly diagram, and this repeats with every sunspot cycle. So yes, the sunspots will drift towards the poles and then start again on the next cycle.
Thank you. From Joe Affleck, this is a question that veers terrifyingly into internal university politics, but I think we can cope. Lovely talk. I was wondering whether, specifically in St Andrews, if the department felt more attached to the maths or physics department, or is the line completely blurred? Secondly, do you find the department applying knowledge of the sun do you find the department applying knowledge of the sun acquired to other star research much? I've just posted that there for your.
Yeah, no, that's fine. Politics, indeed. No, it's not really politics. I think it's historical that our group is kind of home under the Applied Maths division in St Andrews. This is the case for quite a few other universities, but equally many of my colleagues actually belong to a physics and astronomy department in other universities. I think, to be honest, we could be either. And I think what highlights that is the course we teach in solar theory in St Andrews is actually generally a mixture of equal amounts of maths and physics students. And to be honest, it's what's absolutely lovely about the course is getting these students to interact and getting the maths and physics students to use both their maths and their physics knowledge together. I think the other one was, do we apply it to other stars? Yes, we do talk to our astronomy colleagues in the building next door. And we find that there's the occasional PhD student who migrates across the bridge. For those of you who might know the buildings, the maths and physics buildings are linked by a bridge in St Andrews. And we have, so for example, some of the global modeling of the large scale magnetic field that I showed you. There has been a collaboration between the solar and the astronomy groups applying that to other stars as well. So, of course, the ultimate test of all the models we develop for the sun is whether they would work for other stars as well.
Indeed. Yeah, and it's probably worth saying that, I mean, our mathematicians and statisticians crop up in all sorts of interesting places around the university. So the Scottish Oceans Institute, you can find them modelling ocean currents and things, and also the statistical ecologists as well. So I mean, there's some tremendously interesting applied maths and stats going on all around the university. So it's we're privileged to have Ineke and her colleagues doing this work. Peter says, is there any hope that we might be able to predict a coronal mass ejection aiming for the Earth by improving our modelling techniques in the next 20 years?
I would hope so. We can predict them already. It's just that the lead time in our predictions for the moment are not long enough. So, you know, the prediction happens not long enough before the actual CME happens. There are a range of satellites observing and operating for the moment, and I think one of the most exciting ones is a European satellite for the moment called Solar Orbiter. And Solar Orbiter does some of the remote sensing like the images I've shown you today, but what it also does, it's going to go closer and closer to the sun so that it can start sampling some in situ data, so where it really just measures the magnetic fields and the velocities in situ, so that we can start comparing those. Because again, most of what we have data is remote sensing, and you can think of that as an uncontrolled experiment. You know, we can't ask the sun to do something for us. All we really see is the outcome of the experiment the sun has done, and then essentially what the models do is try and guess what the experiment actually was. So we're getting pretty good at that, but what we want is longer lead times. We want to be able to point at an active region that's particularly complex and say, we think there's going to be one of these CMEs in this direction of this intensity in so many days. That's where we need to be so that we can give sufficient warning to, say, satellite operators to put the satellite in some kind of safe mode, rotate it away from the sun, or take the necessary precautions with the electricity grid, for example, so that these things don't happen. So,
I mean, you were saying that, broadly speaking, you generally expect to see something like 3 coronal mass ejections per day.
Yeah.
Of some scale. So, I mean, presumably what you're talking about here is predicting something that is an unusually intense or large event, or what's the current lead time on that?
So the current lead time is really just a few days, but the CMEs that are particularly hard to spot are actually exactly the ones that are directed towards the Earth. You know, the ones in the movie I showed you of this nice bubble going off sideways, well, they're easy to see because they're going, you know, we see them kind of in profile. But if the bubble comes towards you, it's actually it's quite hard to detect. Now it's interesting that you meant, so during solar maximum, we have several of these a day, but the sun has quieter periods near the solar minimum. And I've talked a lot about how this magnetic field of the Earth protects us, but of course there are people who occasionally leave that magnetic field. And there is a kind of an interesting anecdote about how the missions to the moon actually happened during a relatively quiet period. And by coincidence, more than prediction, missed any large coronal mass ejections. There is a nice graph showing when the Apollo missions took place and when large coronal mass ejection happened. And they interlace again more by luck than by actual prediction. Now, of course, if you go to the moon, that's probably doable. But if we're really serious about going to Mars, we have to come up with a clever way of protecting those astronauts.
Yeah, indeed. And so in relatively lower orbit, I suppose, with the International Space Station, do they suffer from disruption?
They would, during a particularly intense magnetic storm, they get warning and they have a room to retreat to that's actually lined with lead to protect themselves. So they do, but that's okay for the International Space Station. Launching lead-based spacecrafts to Mars is unfortunately not practical.
Yeah, I can see how that might be the case. I think we've just got time for. I've got 2 questions left sitting here, and I think we've probably just got time to address those. Peter again says, are there any parallels with the mathematics of weather modelling?
Absolutely, there are actually quite a lot of them because the weather modeling essentially uses the fluids part of the equations that I was describing. Quite a few of our PhD students will end up getting jobs with the Met Office doing weather predictions. Again, it's a large scale system where you're relying on predicting variables and how they're going to behave in space and time. Depending on forces that there are, you know, pressure forces are essentially just winds, and you know, from those we try and predict what the temperature is going to be and model that forward in space and time. So yes, there are a lot of parallels there.
Thank you. And then finally from Max, this is a great question. It's one that was actually occurring to me as you were showing your slide. What's the best explanation to date for the high temperature of the solar corona?
Okay, thank you very much, Max. The best explanation is what I showed you in some of those small scale models. It's magnetic fields interacting. You know, we know just from basic electromagnetism, when magnetic fields interact, you generate currents, and those currents will generate high temperatures. Where we are struggling with our models is to generate the right temperatures or the right currents in the right locations on the right time scales. So, for example, I'll be very honest here, I can do some of these models with the MHD waves that I look at, but the heating is too slow. So I can generate these 1 million degree temperatures, but if I then look at how quickly the sun would radiate this energy away, that radiation beats my generation of these temperatures. So it's that balance between producing these high temperatures in our models, but then doing it on the right time and spatial scales. And that's the bit we struggle with. So we know it's down to these magnetic fields. We still haven't quite got the hang of doing it on the right time and length scales that the sun seems to be able to do.
Got it. Thank you. I said that was going to be the last one, but I've just had another really good question in, which I can't resist asking you. So from Amit, who says, brilliant talk. Thank you. Is solar wind in space turbulent? If so, are the structures and features similar to that of turbulence in the Earth's atmosphere?
I think, again, it's a yes and no. I mean, there's obviously a large-scale structure to the flow out from the sun into interplanetary space past all the planets. But on small scales, we do see turbulence developing, and it's actually one of the places where, again, we can in situ measure that, which I very much wish we could do for the sun as well. But I suspect that's a long way in the future.
I think we'll leave it on that note with the tantalising prospect of measuring the sun's solar winds turbulence. Ineke, thank you so much for that talk. That's been absolutely fascinating and delivered with huge clarity. These enormous questions and enormous effects that you've been describing. I think you've brought them to life for us really wonderfully. So my head's spinning with everything that you've been showing us. It's really wonderful. So thanks so much for taking your time to share all this with us. And thank you also to everyone listening, and to those of you who asked such terrific questions. As ever with the St Andrews community, you can always expect incisive and insightful questioning. So thank you for that. We're going to wrap up now. I just have time to let you know about the next Saints talk, which will be given by Dr. Emma Buckley from our School of Classics, and that will be on Tuesday the 7th of December, also at 5:15 p.m. So hopefully we will see you then. But for now, my thanks again to Professor Ineke Moortel for a really fascinating talk, to you all for listening, and also to the team behind the scenes who've been keeping us all straight throughout the evening. So thank you very much to all of you, and have a very good evening. Thanks.